All right, let's dive into one of the most powerful and, honestly, one of the most elegant ideas in all of machine learning, the support vector machine, or SVM for short. It's an algorithm that totally changed the game for classifying things, and it all kicks off with a really simple, intuitive question.
So take a look at this. Imagine you've got two groups of data points, the red circles and the blue crosses. Your job is to draw a line that splits them up. Now both of the lines you see here, A and B, they technically work. They both separate the points correctly. But which one just feels better? Which one would you bet on?
If you found yourself leaning towards line B, you've already tapped into the core idea that SVMs were built to solve. See, it's not enough to just be right. You want your model to be confidently right. And in machine learning, that confidence is pretty much everything.
This really gets to the heart of what we were just feeling. I mean, look at line A over there on the left. Sure, it's correct, but it's hugging those data points so tightly. If a new point came along that was just slightly off, it could easily get misclassified. But line B, well, it gives itself plenty of breathing room. It's more robust. And that breathing room is the absolute key here.
So how do we find that best, most confident line? Well, the people who came up with SVMs used this fantastic analogy. They said, instead of just drawing a thin line, what if you tried to pave the widest possible street between the two neighborhoods where no house can even touch the pavement?
And this widest street has a proper name, of course. It's called the geometric margin. It's simply the distance from the center of the road, our decision boundary, to the closest points on either side. The wider you can make that margin, the more confident your classifier is, because you've created the biggest possible gap between the two classes.
And that's it. That's the whole game. This is the big optimization problem at the core of every SVM. We're not just looking for any line that gets the job done. We are on a mission to find the one single line that makes that margin, that street, as wide as it can possibly be.
Okay, so if the margin is our street, what actually defines where its edges are? As it turns out, it's not every single data point that matters. Nope, it's just a very, very special few that do all the heavy lifting. And these crucial points are called, you guessed it, support vectors. They're the houses right on the curb of our widest street. They're the ones literally supporting the entire boundary, holding it in place. If one of them were to move, the entire street would have to shift.
And this is what makes the SVM so incredibly efficient. Think about it. It ignores almost all of the data. It only pays attention to these critical support vectors. You could move any of those other points around, and as long as they don't cross over into the street, the decision boundary won't budge one bit. This laser focus on just the toughest, most boundary-defining points is a huge part of what makes the algorithm so effective.
Okay, but let's be real for a second. Data in the wild is almost never this clean and perfect. So what happens when our two neighborhoods are a little mixed up, and you can't actually build a perfectly straight, empty street between them? Yeah, this is where that simple idea of finding the widest hard margin kind of falls apart. If you have even one single outlier on the wrong side of the street, a perfect separating line becomes mathematically impossible. This happens all the time, either because of weird data points or just because the groups naturally overlap a bit.
So to deal with this, we need to be a little more flexible. We introduce the idea of a soft margin. Unlike that really strict hard margin, a soft margin says, you know what, it's okay if a couple of points are inside the street, or maybe even on the wrong side. It accepts that a perfect separation might not be what we want anyway, and this makes it way more robust to outliers and the kind of noisy data you see in the real world.
And we get to control this flexibility with a parameter, which is usually called C. You could think of C as a strictness style. If you crank C way up, you're telling the model there's a huge penalty for every mistake, so it's going to try to create a really narrow margin that gets every point right. But if you turn C down, you're being more forgiving. You're saying, hey, I'd rather have a nice, wide, simple street, even if it means a few points end up on the wrong side. It's all about that trade-off.
And now, we get to the part that takes SVMs from just a clever linear classifier to an absolute powerhouse. What if your data isn't just a little messy? What if it's fundamentally impossible to separate with a straight line?
Just look at this. You have one class of points completely surrounded by the other class. It doesn't matter where you try to draw a straight line. You are never going to be able to separate these two groups. In 2 dimensions, this problem looks completely impossible to solve.
This is where the real magic happens. It's called the kernel trick. It takes this impossible 2D problem and, get this, it projects the data into a higher dimension. Imagine all those points are lying on a flat rubber sheet. Now, what if you could poke the sheet from underneath right in the middle? The red inner points would be lifted up higher than the blue outer points. And suddenly in 3D, you can just slice a flat plane right through the middle and separate them perfectly. The SVM does exactly that, finding a simple solution in a higher dimension, which translates back to a complex circular boundary in our original world.
Now you might be thinking, wait a second, projecting data into thousands or millions of dimensions, that sounds computationally insane. And you'd be right. But here's the truly brilliant part. A kernel function is an incredible mathematical shortcut. It allows the SVM to calculate the relationships and similarities between points as if they were in that super high-dimensional space, without ever actually having to do the impossible math of figuring out their new coordinates. It's like getting all the benefits without any of the cost.
And this is the secret sauce for why it all works. The math behind the SVM only ever needs to know something called the inner product between two data points, which is really just a way of measuring how similar they are. And that means we can swap out that simple calculation with a much more powerful kernel function. By doing that, we get all the amazing separating power of a high-dimensional space without ever paying that crazy computational price. It's so clever.
So let's pull it all together. Support vector machines are this amazing combination of three big ideas. First, they're robust because their whole goal is to maximize that margin of confidence. Second, they're super efficient because they wisely ignore most of the data and focus only on those critical support vectors. And finally, they are just incredibly powerful, able to solve mind-bendingly complex problems by using the kernel trick to look at the data in a whole new dimension.
And that kind of leaves us with a final thought to chew on. The kernel trick proves that a problem that looks totally impossible from one angle can become trivially simple if you just find the right perspective. It really makes you wonder, what other tough problems that we face are not actually hard at all, but are just waiting for us to find a different way to look at them? Thanks for watching.